My dear students, today we are in lecture number 19. Of chapter 2 of electrostatics. My dear student, in last lecture 18, we have discussed about the electric potential energy gradient. I'm giving you one question for the classwork, and then I will start today about the mathematical derivation of electric potential due to point charge. Okay, my dear student, suppose this is a question, this is your classwork. Kindly go to the last lecture number 19. You will find how to solve this question if you have not seen that video lecture. Potential energy, which is the function of a space x, y, z, is given as suppose a constant, positive constant, x square y by z. Okay, and the question is to find the force. Okay, so my dear students, this is your classwork. Today we will start our lecture with the electric potential energy and potential due to point charge. Okay, due to point charge. Okay, my dear student, one concept in last class we have studied, if you remember, or you can go back to see that video lecture. It was work done, or the elemental work done, dW, that we have studied already, F dot dr. This is the vector quantity. Okay, and we will have the total amount of work done from initial to final point. It is the limit. This one we know. Okay, suppose a point charge, we are having either point charge plus q, and from this plus q, actually we are bringing a test charge from infinity. Okay, from infinity we want to find out electric potential energy when this charge, suppose it is q. Okay, this is the small q, when it is r distance from this charge, r distance. When this charge is moving from infinity, it is moving from infinity to a particular point, take an elementary length dr. Okay, elementary length dr. Since we are coming from this side and using the vector, thus dr will be considered with the minus r cap. Okay, my dear student, here it is the positive charge. This charge is positive q and this is the plus q. You are moving this positive charge in this direction. That's why you are taking this dr elementary distance as minus sign, since this is our positive direction and we are moving in this direction, minus. But here the force on this charge will be in which direction? In upward direction. So force will be of F unit vector r cap positive, and dW we will write here F r cap dot dr minus r cap. With proper limit we will get the mathematical expression. Here From where we have to move? From infinity. Initial point is infinity. At infinity, the electric potential and electric potential energy both zero. Remember, my dear student, even if you will try to recall by the definition, if it is the amount of work done by bringing a test charge from infinity, it means if you are moving from infinity, then you are doing some work. It means at infinity, what will be the amount of work? At infinity, the work zero. Means work is to be started from infinity. It means at infinity it is zero. So potential at infinity, remember, it is zero, and potential energy and potential at infinity must be zero. This is the assumption you have to remember. Okay, my dear students, directly that assumption will be used as we are using over here. At infinity, potential energy will be, that is the amount of work done, will be zero, and we have to find at distance r. At distance r, the work done will be potential energy. So dw integrated for w and u minus 0, it will be u. It is equal F, the force between these two charges. Using Coulomb's law, we can write the K Q1 Q2 by R square into dr, and we are using minus sign. Why? R dot R1, but here minus we are taking out from infinity to R. Okay, I don't think so this is a very difficult. You can do calculation by yourself, student. Okay. Now u, it is minus k q, q is constant, taken out, integration of 1 by r square dr infinity to r, minus k q q. Okay, integration of 1 by r square will be minus 1 by r from infinity to r. Okay, so minus k q q minus 1 by r, and minus minus plus 1 by infinity, it will be 0. Minus minus plus k q q by r. This is the potential energy. Okay, so this is the simple derivation of potential energy. But the remarkable thing is, remember, if you have to write in note point, in the system, if this is the charge in the system, you are having two charges. Okay, one, it is q1 1, and another it is q2, separated by distance r. Then potential energy between these two charge 1 and 2, you are writing here the k q1 q2 by r. Remember, if this system having the charge in this way, minus q1, and another is plus q2 with the same distance, then you will write the potential energy 1 2 as k minus q1 q2 by r. Now here potential energy you have to write with the proper sign. If both are negative, then you will write negative negative. If one negative positive, you are writing negative positive. If this is positive and negative, then you will write this positive and this negative. Now if you are raising a question, sir, if this potential energy and work done both are the scalar quantity, why we are taking here the negative sign? Actually this negative sign, students, we are getting mathematically. You can see as we move from infinity to r, we got a unit vector r cap. There were r cap. If this is negative and positive, the direction of force will be changed, and due to that change in direction we will get a sign. That's why we are getting here the positive or negative. But there is no change in magnitude of potential energy. Remember, magnitude is not going to be changed. Magnitude is the same. It is only giving you the concept whether the here the amount of energy, whether the in system we are having the two charges, positive or negative, nothing else. Now students, we will correlate this potential energy with potential also, as we have been studied. So we'll have the derivation of potential, mathematical expression of the potential. Okay, this is also very important, and we should study back to back after this potential energy, that would be the easy expression of potential, electric potential, remember, okay? Electric potential, we used to represent that potential by V. And we know that the potential is nothing but the potential energy per unit charge. Now we have to decide that at which point we want to find out the potential. If you want to find out the potential, suppose this was the charge plus Q. At r distance, we bring a charge from infinity. This is the infinity, suppose. And we are bringing this charge from infinity. We have to find potential at this point, okay, for this point. Then you are finding potential of which charge? Capital Q. Which charge? Capital Q. At which point? This point. It means you have to divide the potential energy by this charge. So it will be Q. I hope you are getting. Potential of this charge at this point, that is at distance r, you can also write at VR, it is K potential energy, K Q divided by R and divided by Q. So this will be cancelled out and you will have the potential at distance R as K Q by R. Okay, my dear student. So this is the mathematical expression for the potential, electric potential. Now, it is also mandatory to correlate the potential. If you have written the potential energy for positive and negative charge, then you should raise the question, sir, can we write the potential also with the positive and negative sign? Then answer will be yes, of course. You have to represent if it is positive charge. Over here, you are finding potential at this point P at distance R. Then potential at P will be plus K Q by R. If you're having minus Q charge and you have to find potential at point P at distance R, then you will write Vp as minus K Q by R. Okay, student. So this is the very important. Kindly make your notes for this one. Now we will solve few simple question, my dear student. The very simple question, and then we will move for the another concept that you have to face in your board examination. Okay, my dear students, kindly note down. I am rubbing this one. Okay, so the very simple question for the potential, and as a student you have studied the superposition principle of force and field. In same way you will study the superposition of potential, electric potential. Okay, it means you can find the net potential, at a point due to number of charges. The simple thing here is that in field and electrostatic force, you have calculated the electrostatic force and field, that is the vector quantity, and it was very difficult to break the component. Not actually difficult, but a little bit lengthy to break the component. But here in potential and potential energy, this is the very simple. You don't have to break the component. Directly you can find the answer. For example, if I'm giving you superposition principle, I'm telling you, as we have been studied, the net potential at any point can be written as or can be represented as the sum of potential due to individual charges. Okay, you don't have to write the vector sum because it is scalar quantity. Suppose the two charges you're having, the two charges Q1 minus Q2 are, you have to find the net potential at P. V net at P is equals to what? Okay, my dear student, it's very simple. You can write here the V net is equals to plus, it is the positive charge K Q1 by how much distance it is R. Now this is negative, so minus K Q2 divided by the distance is 2r. This is 2r. Joule per coulomb is the volt. Okay, or you can also write the joule per coulomb. This is the answer. Very simple, na? Okay. Another question. You have to find potential due to this system. Okay, equilateral triangle. You have to find potential at this point. Minus 5 microcoulomb and this is minus 10 microcoulomb. Okay, my dear students, you have to find the potential at point O, net potential, with proper calculation. 1. Second question. Again, this is the equilateral triangle. The property of equilateral triangle, students, you know that if you will draw a perpendicular drop over here, both the distance will be same. I hope you are well aware. If I'll put a perpendicular drop, it will be equal. Now, if it is plus 5 microcoulomb and minus 5 microcoulomb, what will be the potential at point O? And you will find the net potential, since both the separations are same, so the potential will be of equal magnitude but opposite in nature, and the net potential will be 0. You can see if this distance is, because I'm not giving you the value of this r, whether this is in angstrom or micron. Okay, so this could be very small and this charge is already very small. So could you consider this system as a dipole? Yes. If this is dipole, then what type of this point will be? Yes, this is nothing but the equatorial point. Equatorial point. And equatorial point, at equatorial point you are getting the net potential 0. Okay, student. So after few questions on might be in next lecture, we will study the potential due to dipole, and we'll get the potential at equatorial point due to dipole will be 0. Okay, my dear student. Okay, now the next question. In this similar way, you will find number of questions to find the electric potential or the potential energy. Okay, student. The one more simple question I'm giving you: find net potential at O. 1. This is for your practice. Don't be tense. Minus Q plus Q minus 3Q plus Q. And this distance is 2r. You have to find potential at O. This is the square. And the second one, equilateral triangle, but you have to find potential at center. Minus Q plus Q and minus Q. You have to find potential at O, which is center, and this is also at center. Okay, now few numerical of electrostatic potential energy, my dear student. Okay, as we know that the formula of potential energy is U Q1 K Q1 Q2 by R. And you have to use this formula with proper sign. If the charge is positive, then you have to use here positive. If negative, it should be negative. Okay, so the first example, if you are having two charges as 2 coulomb and minus 2 coulomb, this is the very big charge, at distance 1 meter. What will be the potential energy? So the potential energy between these two charges, that is for this system, potential energy we will find of the system. Remember, in this system the total energy is stored, it is the potential energy. So it is the potential energy K Q1 Q2, it is the 2 times 2, it is the 2 coulomb into minus 2 coulomb divided by 1 square, it is 1. So the 4k joule minus 4k joule, this is the answer. Now the one thing, student, as you will move this charge towards the minus 2 coulomb, what will be the amount of work done, whether it will decrease or increase? Try to just analyze by yourself. If you will pull this 2 coulomb charge towards this negative 2 coulomb, what will be the potential energy of the system, whether it will increase or decrease? This is my question. Okay, try to analyze by yourself, and of course give your answer in comment, or just give your answer on the group. Okay, student. Now the next one, student, we are going to study over here the energy for association or dissociation, or the work done to associate the system. Associate or dissociate, okay, the system. As we know that the work done is nothing but the minus delta U, and this minus delta U, it means U final minus U initial, we have written already, which is U initial minus U final. You have to remember this formula. Okay, now the example, this will give you the answer. Example, this is okay 2 coulomb and minus 3 coulomb, okay, minus 3 coulomb at distance 2 meter, at distance 2 meter, and this is a system. This is a system. You have to find the work done to just dissociate this system and bring this charge 2 coulomb at 1 meter. How much work you have to do to bring this 2 coulomb at 1 meter from 2 meter? Okay, now the final system will be this, like 2 coulomb minus 3 coulomb, and distance remain 1 meter. So how much work you have done to bring this charge from here to here? This is the question. If you can solve, try to solve, my dear student. Simply you have to find both the potential energy, and that the potential energy difference will give you the work done. Okay, my dear student. So I'm writing over here, the answer is initial potential energy. Try to find out the initial potential energy was, it is K Q1 Q2, directly I can write 2 coulomb minus 3 coulomb, it is minus 6 divided by 2 square, it is 4 joule, and U final, now K times again 2 times 3 minus 6, but the distance is now 1 meter square, sorry, K Q1 Q2 R, I think, no, it is 2, and here 1 itself. Okay, so it is minus 3k joule U initial, and U final minus 6k joule. So the work done, U initial minus U final, how much it is? It is 3k joule, and 3k joule positive, it means work is done by the system. Of course in the system this charge is full, there is positive charge which shows the positive 3 k joule. In exam, if the questions are coming in this way, you will put the numerical value 9 times 10 power 9. Okay, and joule you can calculate. In same way, if you understand, try to solve this question I'm giving you. This will be your homework. Two coulomb, 1 coulomb, and minus 3 coulomb. The simple question one I'm giving you. Minus 2 coulomb, minus 8 coulomb. At 2 meter, you have to dissociate this charge. The system has to bring this minus 2 coulomb at 1 meter. Okay. Now student, if you are finding the potential energy between number of charges, then bear in your mind, if you are having 3 charges in this way, Q1, Q2 and Q3 as R1, R2, R3. So the potential energy, you have to write the terms of potential energy, how many terms will be there. Here the potential energy, concept of potential energy, try to focus over here. Okay. In this system, we don't have energy, okay? We don't have work. From infinity, we are bringing our test charge, Q1. Whether in this system we are having the potential energy, answer is no. We have potential only, not the potential energy, because there is no any other charge, and for that presence of charge against that electrostatic field, it has to do the work. Okay, so there is no charge, so there will be potential. If you again bring a charge, it is Q2 at distance R. Now there will be potential or potential energy. Exactly, there will be the potential energy, and then you will write here the U between 1 and 2 as K Q1 Q2 by R. Am I right? Yes. Now again, if suppose another charge is bring at this point, separated by the same distance R and R. Now this is Q3, then what will be the amount of work done? As this charge was present, there was potential. As this charge bring Q2, this Q2 has to do the work against the field of Q1. But as this Q3 is to bring, it has to do the work against the field of Q1 and Q2 both. Okay. In this space, there was already potential energy. How much? It was this one. But due to bringing this Q3, new 2 terms will be added in this potential energy, because energy neither create nor destroy. So this will be remain at that place in this system, and the new 2 terms, because it has to do the work against this field and this field also, about against the field of discharge and discharge also. So the new 2 terms will be added, and the net potential will be U12, that is the potential energy between 1 and 2, potential energy between 3 and 1, and potential energy between 3 and 2. Okay. Now this is the total energy. In the same way, you have to solve such type of question. For example, if you will solve this question, the total term will be how much? Directly I am writing you, my dear student. The U total will be K Q1 Q2 by R plus K Q2 Q3 by R plus K Q3 Q1 by R. Okay, and this will be the total energy. Okay, my dear students, so this is all about the today lecture. In next lecture we will study few more concepts of potential, energy and potential. But the main topic of next lecture will be the relation between electric potential and electric field. Okay, that will be the field gradient and potential gradient. Thank you, my dear students.